ethers. What are ethers? The groups, like when you see the compounds of the kind RO, R dash, these are called ethers. They are obtained by different ways. So they are like they are you have this one C2H5O C2H5. So the naming wise, it's like alkoxy alkane. Alkoxy alkane. This is how we named it. So this is ethoxyethane. Ethoxyethane. This is called diethyl ether. And now when these are like symmetric ethers, suppose this CH3O CH3 is there, that is dimethyl ether. Okay. When you have C2H5O C2H5, this is C2H5O CH3. Suppose you have CH3, then that is ethyl methyl ether. Methyl ether. So this is how you have things. So let us write some compounds. You can note it, Amma. Let us write some compounds then of ethers. Okay, Amma, right. So you have okay, not that much required. We will do. So here, while naming oxygen, the oxygen along with smaller alkyl group is said. Smaller alkyl group. Smaller alkyl group is connected to alkoxy. Suppose you have this like the CH3O C2H5. The smaller one is CH3O. CH3 is a smaller alkyl group. So we'll say methoxyethane. Methoxyethane. Suppose you have C2H5O C3H7. So we'll write ethoxy. This one is the smaller compared to this, right? So ethoxypropane. So this is how we name the ethers. That is one thing. Now we'll solve one question. This I feel this sometimes they're asking this for ethers. That's why I want to do the IUPAC also. So we'll do this. So the first one is CH3O CH2 CH single bond CH3 CH3. It is given like this. Now the smaller of this one is methyl, so we'll write methoxy. Okay, in fact one methoxy will write one methoxy. This, if you number the chain, this is 1 2 3, so that is 2 methyl 1-methoxy 2-methyl propane. Another one, we'll take an example. C6H5O C2H5. Out of these two, C2H5 is smaller one. So we'll write ethoxy benzene. Ethoxy benzene.
Okay.
Next one. So you have another one is like benzene is connected to CH2, 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 1, 2, 3, 4, 5, 6, 7. It's connected like this. Okay. Now this is phenoxy. This is a smaller one compared to this. So it is phenoxy heptane. Phenoxy heptane. And now the next one is C2H5O C4H C4H10. So this one is ethoxy butane. So like this we can give the names of ethers. Okay. Now, what is the structure of ether? The structure of ether is like this. So it's like this one carbon. So on the oxygen there will be two lone pairs. It is like you have water molecule, no? You have water molecule. This one you have to know. Suppose I replace one H with R, H with an alkyl group, I will get an alcohol. This H is also replaced with R, I will get an ether. This one you have to know. Water molecule, one hydrogen if I replace with R, I will get an alcohol. Both the hydrogens are replaced with R, then I will get an ether. So that is this one. This is the ether linkage. Ether linkage. So that is oxygen is sp3 hybridized. Oxygen is sp3 hybridized. That's another important thing here. Clear, Amma? Go ahead.
Yes, sir.
Preparation of ethers. Preparation of ethers. Preparation of ethers. So here, by dehydration of alcohols. First one is by dehydration. By dehydration of alcohols. By dehydration of alcohols. This is one method of preparation of ether. So you take, what we do is C2H5OH, two molecules you take, or else you can think of two moles, C2H5OH, and now remove water out of it. Water removing agents are there. They're called dehydrating agents. Dehydrating agent. Dehydrating agents. they can remove water. They can remove water from a molecule or a set of molecules, or a set of molecules. So these are called dehydrating agents. So what they do is they will remove water from two ethers to give two alcohols to give ether. So it is C2H5 O C2H5. This is how you get. So here concentrated H2SO4 is used at 413 Kelvin. This temperature is very important. These temperatures are very important. 413 Kelvin, concentrated H2SO4.
Okay, sir.
Now there is a small change when we do C2H5OH. It's just the temperature, it's very, very important. Concentrated H2SO4. And when you heat it to 443 Kelvin, you get an alkene C2H4, okay, plus H2O. That is dehydration within the molecule. This is like, this is very important. Dehydration within the molecule. When you go to 443, at 443 Kelvin, this is very important step, Amma. So what you have here is, this will be little bit confusing, but you have to remember the water will be lost like this at 443 Kelvin and concentrated H2SO. So when you have this, it is like this. If you have 413 Kelvin, so that one also will write. So once noted, I will write 413 Kelvin what happens, and then the mechanism of this reaction. That also will be.
Noted, sir.
Now, at 413 Kelvin, so how the diethyl ether is formed, that we will see by mechanism. Sometimes they are asking the mechanisms in the examination, so we'll see that. So we have CH3, CH2OH. The first step is protonation of alcohol. Protonation of alcohol. So the protonation of alcohol, this is the first step. So you have the alcohol, and here the proton is coming from H2SO4. H plus is coming from H2SO4. And now here this lone pair will go and stick to this proton will be stick to this oxygen. A lone pair will be transferred here. And now here you get CH3, CH2, OH, H plus ion. This is what you get, right? Now we get, after this we get CH3, CH2, you have OH2 plus And now another molecule of ether, will go and hit here, and then water will come out. Okay, this happens via SN2 mechanism. So when it hits here, water molecule will go out. This is second step, that is nucleophilic attack. This step is nucleophilic attack. By unprotonated alcohol, molecule on protonated alcohol, This is the second step. So when this happens via SN2, substitution nucleophilic bimolecular mechanism. It will happen because it is primary carbon. Primary carbons, they have a tendency to undergo SN2 reaction. So this is second step.
Yes, sir.
Okay, now next one. So the third step is formation of okay, the attack, okay, I can mingle with the second step, formation of protonated ether, that is protonated ether. We are continuing the second step only. So what happens here is CH2, OH2 plus, and then you have this attack, water molecule is lost, and then you get this one. This is called protonated ether or protonated ethoxy ether. This is protonated ethoxy ether. And now the third step is proton is lost to give this one, ethoxy ether.
Yes, sir.
Now what happens next is this protonated ether is there, no? Protonated ether. And you have H2O here. H2O will pick this to form ether. To form ether plus H3O plus. Next one, order of dehydration of alcohols. Of alcohols will follow primary greater than secondary greater than tertiary. This order they will follow. So there are certain limitations for this. I don't want to uh, confuse you and make more deep into that.
Okay.
Okay, no? For board level, this will do. For JE, you have to go little bit JE or medical, little bit depth more you have to go. Next one is Williamson synthesis. What is Williamson synthesis? It, we can make asymmetric ethers with this method. Dehydration of alcohols will give symmetric ethers. That is a limitation actually. Dehydration will be good, I should say, will be good to prepare symmetric ethers. That's the actual limitation what we have with the dehydration. To overcome this, Williamson synthesis will be done to overcome this problem. So this is one of the best method to make the asymmetric ethers. What is the method is, suppose I will take C2H5Cl. This is called, I would say this is called substrate. This is the substrate. And then we use CH3 CH2 O minus Na plus. What is this? This is called sodium ethoxide. Sodium ethoxide. And then you get C2H5 OC2H5 plus NaCl. I'll tell you entire thing what is the process will do. First one is
Okay.
now we have this one. So suppose asymmetric ether we'll consider first. So to prepare this asymmetric ethers, so for example, so here the substrate normally substrate choose primary alkyl halide. This is one important thing. Substrate always choose primary alkyl halide. The reaction undergoes by SN2. So we will do SN2 reaction. We'll take this in this way. So here, let me consider. So I want to make methoxy. Suppose take this one. CH3O. This one I want to make. So how do we name this? 1-methoxy. This is 1-methoxy. 1-methoxy. I would say this is not 1-methoxy. I should say this is the chain. So this will become 2-methoxy, right? 1, 2, 3. Yeah, 2-methoxy, 2-methoxy, 2-methyl propane. So this is the compound I want to make. Okay, this is actually common name is tertiary butyl methyl ether. Okay, tertiary butyl methyl ether. So I want to make this. So for that, what is the process? So choose always primary alkyl halide as the substrate. Nucleophile is bulk one. Nucleophile is always bulk group. Bulk group. This is always the good thing. I will tell you what is that one by one. Let's note this first.
Okay.
Now, how do we do this? So our target molecule is right here first. This is our target molecule to prepare. Now I told you the substrate is the smaller one. Okay, smaller one is substrate. So the first thing I'll do is methyl bromide. This is what I will take. This is my substrate. Now the other part is this one. That is tertiary butoxide anion I have to make. So for that, what they do is, this is called tertiary butyl alcohol. So tertiary butyl alcohol is treated with sodium and dry ether. Okay, sodium in alcohol also you can use, whatever. Sodium, it is treated. And then what happens is, sodium will replace the hydrogens to form this one. So this is what you get. This is called sodium tertiary butoxide. First, what happens is the oxygen, they will ensure that they gains negative charge, and this acts as nucleophile. This part acts as the nucleophile. This part acts as nucleophile. This part acts as nucleophile. Okay, am I clear? Now, once finished, please let me know.
Noted, sir.
Now, we have to do nucleophile plus substrate. Now that is this one, CH3C O minus Na plus. So O minus will write, Na plus will write later. So first to understand this Na plus part later. So this is my nucleophile. You have CH3Br here. And now this O minus, this will hit here and the bromide is out. So you get simply CH3, CO, CH3. Okay. Always remember, The bulky group is, so Br minus is taken by sodium, so you get NaBr. No problem with this one. Br minus will go, this will go and hit from backside, and this is SN2 mechanism. And now always this one for Williamson synthesis, always choose the bulk one as nucleophile. Bulk one as nucleophile. This is the principle you have to remember while doing Williamson synthesis. So we got the target compound, target product that we obtain. The problem, if I do the other way, what happens? There is a problem. Okay. Now, what if I do the other way? This is also very important. Suppose I take this one. This is tertiary butyl bromide. And I will take CH3O minus Na plus. So in principle, I have to get the product. Like CH3O minus, it has to go and react here, and bromine is out. I should get the same product. But this will not work. Reason: secondary and tertiary alkyl halides due to steric hindrance, due to steric in secondary and tertiary. This is very important. In secondary and tertiary alcohol halide due to steric hindrance. What is steric hindrance? Because of these CH3, these groups are there. No, these groups will stop the incoming nucleophile. So that is called steric hindrance. Okay. Elimination will happen. Elimination will happen instead of substitution. Instead of substitution, elimination will happen. That's most important. This one also you have to remember. The CH3O minus acts as a very good base. So something else will happen. What is that? Please note it up to this point. I will tell you what is that other reaction. Okay, ma? Can I clear?
Yes, sir.
Okay, ma. So you have this. So what will happen here is this. So you have this will pick up proton from here and causes the elimination. This is what happens. So because of this, you get an alkene. This is how you get. And now one more reaction we'll do and we'll close. Amma, you are going to school today?
No, sir.
Oh, okay, fine. I'm fine. So this one is there. Suppose this is phenoxide. So you have this the other one. The phenoxide reacts with C, C2H5Cl. So it's the same Williamson synthesis. So it attacks here, chloride is out. So you get, so this out. So you get epoxybenzene by this way. Okay. Another method of preparation of ethers is like alkyl halides with dry silver oxide. With dry silver oxide, that is Ag2O. It forms ethers. So how do we do that? It's like this. CH3, CH2Br, two molecules. And you have silver oxide, which is silver oxide is like this, AgOAg. It will remove the bromines and oxygen will be connected here. So this is how you can remember CH3, CH2O, CH2, CH3. So this is my diethyl ether. This is my diethyl ether. Plus 2 AgBr. 2 AgBr.
Okay, sir.
Next one more preparation is like this from Grignard reagents. From Grignard reagents, we can prepare ethers from Grignard reagents. So the Grignard reagents are a little bit different this time. So what do they do is CH3O, CH2Cl. This is what we do. This is what we take. And then we'll add CH3MgBr. Okay, we'll take CH3MgCl. That is fine. And now what we do is, so CH3MgCl will give Cl minus, CH3 minus. CH3 minus will go and hit here and Cl is out. And it will get attached to MgCl. So what you have to do is connect the positive to negative, negative to positive. Here in this case, CH2, this is positive and Cl minus is negative. Negative to positive, you connect. So what you get? MgCl2 when you connect negative to positive. This is the positive part. and negative to positive, and again. So plus CH3O CH2 CH3. This is how you get from Grignard reactants. So of course they use some THF that is called tetrahydrofuran. Don't worry too much about that. This is tetrahydrofuran. It looks like this. A pentagon shape with oxygen here at one end of the pentagon. Actually, this is called furan. This is called furan. And then when you reduce it further, you will get tetrahydrofuran. This is called tetrahydrofuran THF. Don't worry too much about that. They may give in the exam this THF. Okay, now. So the next one is ethers lower members. You can write lower members are soluble in water. Are soluble in water. Okay, are soluble in water because of hydrogen bonding. Because of hydrogen bonding. They are soluble in water because of hydrogen bonding. So how do they look like? Hydrogen bonds is like this: R, O, R, and then you have the water molecule, just like this. And then you have water molecule, just like this, and then they get attached to oxygen. It is something like this. They get attached to oxygen. So that's how it's soluble. This is a hydrogen bonding. This is how you get hydrogen bonding of ether with water. Hydrogen bonding of ether with water. Clear, Amma? Next. Next, we have some chemical reactions of ethers. Chemical reactions of ethers. What are the chemical reactions of ethers? So there are some few reactions. So for example, if you have C2H5 O C2H5, suppose it is reacting with the hydroiodic acid concentrated. So it's some temperatures like 373 Kelvin. In first step, you get C2H5I plus C2H5OH. This is what you get in the first step. And now the C2H5OH, what you get is like you break this, you put one hydrogen or oxygen, you put iodine here. That's it. That's how in the initially. And then C2H5OH, and again you treat with HI, you get C2H5I plus, that's it, C2H5I plus H2O. This is what you get. So concentrate HI, how to do this, I will tell once again. One more example we'll take and do once you finish this. But this will not happen. The second step will not happen when you have the aryl groups. This step will happen only for alcohols. Alcohols, this step, the second step will come for alcohols. Second step will not come for phenols.
Right.
Okay, we'll do that. The next one is, suppose I have like this. Suppose I have like this. Suppose I treat this with HI at 373 Kelvin. What I have to do, break this bond, give hydrogen to oxygen, iodine for CH3. Simply like this you can remember. So you have phenol plus CH3I. So the thing is that in the phenol further this reaction will not take place. Phenol plus HI, this reaction will not take place any further. So up to here it will stop. At this point it will stop. That's why two steps will write. Now order of reactivity of acids. Order of reactivity of the acids is like HI greater than HBr greater than HCl. This is how you get the order of reactivity. This is a huge mechanism inside. Don't worry too much about the mechanism.
Okay.
Okay, right. Now these things will undergo electrophilic substitution reactions. Further things like if you have the OCH3 kind of things. So when you treat this with Br2 and in ethanoic acid, okay, you have Br2 acetic acid. This is one important reaction. Here OCH3 group is orthopara directive. Orthopara directive. So it will give the bromine substitution will happen at the ortho. The bromine substitution will happen at the para position. Bromine substitution will happen at the ortho. Bromine substitution will happen at the para position. Okay, ma? So this one is called ortho bromo anisole, and this is called para bromo anisole. Because these groups are away in the para position, this is major product because of less repulsions. This is minor product because of more repulsions. Generally, ortho product will be minor, para product will be major. This one you can remember.
Okay, sir.
Okay, ma. Up to here it is sufficient. So we will. I will tell you about tomorrow class. Okay, ma. So maybe this time is it fine? Tomorrow also one more.
Okay, sir.
Okay, ma. Right. Bye.